Welcome to the deep dive. Today, we're embarking on a pretty epic journey, actually. We're tracing humanity's long relationship with iron and steel.
Right, millennia of history here.
Exactly. And we're not doing a dry lecture. We're digging into our sources to really get the core story, how these metals basically shaped everything.
From, ancient times right up to today's technology.
We'll follow it chronologically, looking at the inventors, the workers, the big industry players, the whole picture.
And the starting point is genuinely surprising. It's not from digging it up initially.
We're from them.
From space, actually.
Yeah.
Meteorites.
Seriously, iron from meteorites.
Yeah. Around 3200 BCE, ancient Egypt, we found these iron beads in tombs at Giza. They're made from meteoric iron.
Wow. So they call them gifts from the more than gold. That's hard to wrap your head around.
Think about King Tut's dagger. The famous one?
Yeah.
That's made from meteoric iron from the 14th century BCE. A pharaoh with a dagger, literally forged from a star.
Okay, that is an amazing start to the story. So this super rare space metal, how did we transition to getting it from the Earth?
Well, that seems to be the next big step. Around the middle of the second millennium BCE, maybe 1500 BCE or so,
Okay.
over in West Asia, possibly Anatolia, where the Hittites were,
Yeah.
they figured out how to smelt iron, or the stuff you dig up.
Smelting, so heating it up to get the metal out.
Exactly, using early furnaces. And there's this legend that the Hittites, kept it a secret for a while. Their iron weapons gave them a bit of an edge.
One military secret. But secrets like that don't usually last, do they?
Not forever, no. Around 1200 BCE, things got chaotic. The Bronze Age collapse.
Yeah.
And during that upheaval, iron production started to spread much more widely.
Ah, so that's the real beginning of the Iron Age proper.
That's pretty much it. Iron tools, iron weapons,
Mm-hmm.
they become much more common. And it was a better material in many ways.
How so? Better than bronze?
Yeah, it was harder, for one. And crucially, you could sharpen it to a finer, more durable edge. Think sharper swords, but also, maybe more importantly, better farming tools.
Right, stronger plows could work tougher ground. That would boost food production.
Exactly.
Yeah.
It wasn't just about warfare. But what's really fascinating is that this wasn't only happening in West Asia,
Oh,
sub-Saharan Africa.
yeah.
There's evidence suggesting iron smelting might have developed there independently, maybe even earlier.
Earlier than the Hittites.
Potentially.
Mm-hmm.
We've got sites in places like modern Cameroon and Nigeria with evidence dating back between 2000 and 1200 BCE.
Wow.
There's a site called Obu in Central Africa. Furnaces, tools, dated as early as 2000 BCE using radiocarbon.
That really changes the narrative, doesn't it? Africa as a potential birthplace of iron tech.
It certainly adds a whole new dimension, and it wasn't just small scale. Look at Meroe in Sudan. By the 6th or 5th centuries BCE, they had large-scale iron production. You can still see these huge mounds of black slag, the waste product there today, miles of it.
Industrial scale, way back then. What kind of furnaces were they using in Africa?
Mostly what we call bloomery furnaces, often smallish clay towers, kind of chimney-like. They'd eat the ore and charcoal inside. But there was actually a lot of variety in furnace design across Africa, adapted to local conditions.
Okay, so the bloomery furnace, that seems key to the whole Iron Age. Can you break down how that actually worked?
Sure, so imagine this clay structure, maybe waist-high or taller. You load it with layers of iron ore and charcoal.
Right.
Then you get it really hot, maybe 1200 degrees Celsius. The charcoal does two things. It's the fuel, obviously, but it also acts as a reducing agent.
Meaning it pulls the oxygen away from the iron ore.
Exactly. It chemically separates the iron. What you end up with isn't molten iron, though. It's a spongy, red-hot mass of iron mixed with impurities called slag. That's the bloom.
A bloom. Okay, so not quite usable metal yet.
Not yet. That's where the blacksmith comes in. This is hard, skilled work.
I bet.
The smith takes the hot bloom, reheats it, and hammers it again and again. This hammering does two things. It squeezes out the molten slag, and it compacts the iron particles together into a solid bar or shape.
So lots of heating and hammering. Sounds exhausting.
It was incredibly demanding. Smiths often worked in low light, dawn, or dusk, so they could judge the metal's heat by its color. They were often highly respected figures, sometimes seen as having almost magical powers.
Transforming rock into metal. I can see why.
Yeah, and in some cultures, like in parts of Africa, the whole process had ritualistic meaning. The furnace seen as a womb, the iron being born.
Yeah.
Really deep symbolism.
That's fascinating. Okay, so iron is spreading. People are making it with bloomeries. How did this start changing societies? You mentioned the Assyrians.
Right, around 1000 BCE, the Assyrian Empire really shows the impact. They embraced iron technology for their military in a big way.
How so?
Well, iron weapons and armor were harder than bronze, sure. But crucially, they were also cheaper to make and could be produced in much larger quantities.
Ah, mass production, relatively speaking.
Exactly. So the Assyrians could equip huge armies with decent weapons. We hear about one king around the 7th century BCE equipping his entire elite guard, like 10,000 guys, all with iron.
10,000 soldiers with iron weapons. That's a serious force multiplier back then.
Absolutely. It changed the scale of warfare.
Wait,
Allowed for bigger armies, longer campaigns. It helped redraw the map of the ancient Near East.
so a definite military advantage. But it wasn't just war, right? You mentioned agriculture earlier.
Definitely not just war. Iron tools just made everything more efficient. Stronger plowshares, better axes for clearing forests, sickles for harvesting, iron nails for construction.
It boosts the whole economy.
Pretty much. More food means larger populations, bigger settlements, and this tech spread. In Europe, you had tribal societies like the Celts mastering ironworking.
The Celts, right. Their metalwork is famous.
Yeah, by 500 BCE or so, their Latin culture produced amazing wrought iron stuff, swords, jewelry, tools. Europe was well into its Iron Age.
Okay, let's shift focus eastward again. What about South Asia, India?
India also gets into the Iron Age around this time, maybe starting around 1200 BCE in the Ganges Plain area.
Similar timing to the spread in the West. Was it connected?
It might have come via trade routes from West Asia initially, but India definitely developed its own innovations pretty quickly.
Oh.
And Indian iron, and later steel, gained a serious reputation for quality.
Really? Even that early?
Oh yeah. By the time Alexander the Great gets there in the 4th century BCE, Greek writers are already talking about how good Indian iron is. Alexander supposedly even got a big gift of Indian steel.
A gift of steel? That tells you something about its value.
Doesn't it? And beyond prestige items, iron was vital there too. Farming, obviously, but also equipping the armies of big empires like the Magadha and the Mauryas. Iron weapons were key to their power.
Okay, so India's making high-quality iron. Now, China. Our sources suggest they had a really unique path, right?
Very different, yeah. China seems to start a bit later, maybe 6th or 5th century BCE, according to traditional accounts. But once they get going, they advance incredibly fast and in a totally different direction initially.
How so?
Around the 5th century BCE, maybe in the state of Wu, they accidentally achieved much higher furnace temperatures, around 1130 degrees Celsius.
And what did that higher temperature do?
It fully melted the iron. This was revolutionary.
Molten iron. Why was that such a big deal?
Because when the iron melted, it absorbed a lot of carbon from the charcoal fuel, maybe around 4%. This high carbon iron melts at a lower temperature, and crucially, you can pour it into molds.
Ah, cast iron.
Exactly. They discovered cast iron. Suddenly, instead of laboriously hammering a bloom into shape, you could cast complex shapes relatively easily and quickly. Tools, pots, plowshares, even parts for structures.
That's a massive leap in production efficiency.
Huge. We find cast iron artifacts in Jiangsu province from that early period. And the key thing is, China developed blast furnaces capable of producing this molten cast iron and mass millennia before anyone else.
Millennia.
Roughly 2,000 years before Europe rediscovered blast furnaces. China was mass-producing cheap, useful cast iron, while most of the world was still focused on wrought iron from bloomeries.
2,000 years. That's just staggering. But cast iron, isn't it quite brittle? Not great for everything.
It is brittle, yes. Good under compression, but snaps under tension or impact. Not ideal for swords or things that need to flex.
So did the Chinese figure out how to deal with that?
They did. They became masters of manipulating the carbon content. They developed ways to convert that brittle cast iron back into more useful forms.
Like wrought iron or even steel.
Exactly. One key method was decarburization, basically reheating the cast iron in air to burn off some of the excess carbon, making it more like wrought iron.
So they can make both cast iron and wrought iron efficiently.
And early forms of steel, too. By the Qin dynasty, 3rd century BCE, they were making quench-hardened iron swords. We found warrior graves from around 250 BCE with weapons made from a whole range of stuff. Wrought iron, medium carbon steel, high carbon steel. They understood heat treatment.
That implies a really sophisticated understanding of the material.
Absolutely. And then under the Han dynasty, production went into overdrive. The state made iron a monopoly, built huge blast furnace complexes, essentially early industrial ironworks.
How big are we talking?
Some of these complexes could produce tons of iron per day.
Tons, compared to maybe kilograms from a Roman bloomery?
Exactly. The scale is just completely different. And the Han refined their techniques further, using methods kind of like later European puddling to refine pig iron into higher quality wrought iron or steel.
And the impact.
Massive. It equipped their powerful armies, boosted agriculture, construction, everything.
Mm.
By around 200 CE, China arguably had the most advanced iron and steel technology in the world.
Yet all this amazing Chinese innovation, it didn't really spread west at the time.
Yeah.
Romans and Greeks didn't know about cast iron.
Seems not. The Mediterranean world largely stuck with bloomery-produced wrought iron. Roman legions had their iron gladius swords, often steel-edged through case hardening or clever forging, and iron armor.
So they were skilled blacksmiths, the Romans.
Oh, definitely. Roman smiths knew how to work wrought iron very well, including quench hardening and tempering to make steel for edges and tools. But the scale was just so much smaller than Han China. No mass-produced cast iron, no state-run blast furnace complexes.
So the West is making wrought iron, maybe small amounts of steel. But that quest for really good steel, that harder, sharper metal, continued everywhere.
Yes, smiths everywhere knew that somehow heating iron with carbon-rich stuff made it better, tougher, sharper, steel. But how to do it reliably and consistently, those were often closely guarded secrets.
Like trade secrets passed down through families or guilds.
Exactly. Often wrapped in a bit of mystique or ritual, too, to
Never.
protect the knowledge.
And one of the most legendary early steels comes from India again, right? Wootz steel.
It's steel, yeah. Incredible stuff. Originating in South India, maybe as early as the first few centuries CE, possibly even earlier, it was a high-carbon crucible steel.
Crucible steel, how was that made?
It was a really clever process. They take high-quality wrought iron, put it in small sealed clay pots crucibles, along with specific carbon sources, like certain woods or leaves.
Okay.
Then they'd heat these sealed crucibles in a furnace for a long time at very high temperatures. Inside the pot, the iron would melt and absorb carbon very evenly. When it slowly cooled, it formed a small ingot of very high carbon steel, usually 1 to 2% carbon.
A uniform high-carbon steel ingot. And this was traded.
Oh yeah, it was highly prized. Ancient writers in the Mediterranean mentioned this amazing meteoric steel or Indian steel. These wootz ingots were exported.
And these wootz ingots, they're the key ingredient for the famous Damascus blades.
That's the connection. Swordsmiths in the Middle East, especially places like Damascus, got hold of these wootz ingots that they called it fulad or hinduani and developed special forging techniques.
What was special about the forging?
They worked the steel at relatively low temperatures.
Yeah.
This careful process revealed the steel's internal structure, creating that characteristic watery or patterned look on the blade surface.
The Damascus pattern.
Exactly. And these blades became legendary, especially during the Crusades. Europeans were amazed by them. Tales of swords that could cut silk scarves in midair or chop through lesser swords.
Some exaggeration, perhaps, but based on a superior blade.
Definitely. Modern science confirms that genuine Damascus blades made from wootz have this unique microstructure with bands of hard carbides, giving them that amazing combination of a super sharp edge and toughness.
Making wootz sounds like it required incredible skill.
Absolutely. Precise temperature control, the right ore, the right mix of carbon materials. It was high art as much as craft. And India was exporting this true steel by the 6th century CE, maybe earlier.
You mentioned records of this trade.
Yeah, an 11th century Persian scholar mentions Indian steel coming through Kollam in Kerala. And later, Arab travelers like Idrisi in the 12th century wrote about how Hindu smiths excelled at making steel, the best in the world for fineness and temper. They called it hinduani.
So the Damascus saber is really a product of Indian material science meeting Middle Eastern craftsmanship, a cross-cultural achievement.
Perfectly put. Damascus became famous because its smiths knew how to work this amazing imported Indian steel. The Crusaders encountered it, were blown away, and took the stories back to Europe.
Did Europe learn how to make crucible steel then?
Not immediately, no. The secret wasn't cracked for centuries. But those legends definitely spurred interest in later research, eventually helping European scientists understand the role of carbon in steel. It's funny how analyzing wootz actually helped advance European metallurgy much later.
A long feedback loop. So we had crucible steel in India and Persia, decarburized cast iron in China. Any other early steel methods worth mentioning?
Well, there's also crucible steel in Central Asia, similar processes. And in Japan, they developed their own complex bloomery-based method to create tamahagane, the layered steel used for samurai swords. Different paths to a similar goal.
Okay, let's swing back to medieval Europe. They're still mostly using bloomeries after the Romans leave.
For a long time, yes. Blacksmiths were vital, working wrought iron. They knew about Damascus steel, imported it, or tried to mimic the look with pattern welding. But then, around the High Middle Ages, maybe the 13th century, something big changes.
What's that?
Europe independently reinvents the blast furnace.
The blast furnace, again, where did this happen?
The earliest evidence points to places like modern Belgium, or maybe Switzerland. These were taller than bloomeries made of stone, and crucially, had better bellows, often water-powered.
More air means hotter temperatures.
Exactly. Hot enough to produce molten high-carbon iron, again, pig iron, they started calling it.
Pig iron? Why that name?
Apparently, the molten iron was often run out into sand molds that looked a bit like a sow nursing piglets. A bit strange, but the name stuck.
Okay. And when do we first see cast iron being used in Europe from these furnaces?
The earliest definite record is around 1350, cast iron cannonballs in Burgundy, France. By the 1400s, blast furnaces were spreading, especially for making cannons and shot. Gunpowder warfare was driving demand.
So Europe enters its cast iron age, but like 1700 years after China.
Roughly, yeah. It's a fascinating case of independent invention and technological lag, or perhaps different priorities.
And just like in China, this European pig iron was brittle. How did they make it into useful wrought iron?
They developed what's called the finery forge. You'd take the solid pigs of cast iron, remelt them in a special hearth with an air blast to burn off excess carbon.
Similar to the Chinese decarburization idea.
Sort of, yeah. Then the semi-solid iron mass was hammered, often with large water-powered trip hammers, to squeeze out impurities and consolidate it into wrought iron. It was a two-step process. Blast furnace makes pig iron, finery forge refines it to wrought iron.
And this led to a bigger European iron industry.
Definitely. By the late medieval period, places like Sweden, with its great ore, and the Rhine Valley were major iron producers, but it came at a cost. Deforestation for charcoal was becoming a huge issue. Water power became essential for the bellows and hammers.
And this better iron, and maybe some steel, shows up in late medieval warfare.
Oh yeah. Think knights in full plate armor, which needed steel components. Think steel-tipped arrows, like the English longbow arrows at Agincourt that could pierce armor.
And then firearms really increased demand.
Massively. Cannons, muskets. They needed tons of iron and eventually steel. This pushed foundries to experiment, trying to cast better cannons. Guys like Jean Touligny in France, Ralph Hogg in England in the 16th century were pioneers here.
Were people starting to study this more scientifically yet?
We see hints. Leonardo da Vinci around 1500 sketched furnaces and actually noted the difference between cast iron and steel.
Yeah.
And in 1556, Agricola's book De Re Metallica documented mining and smelting really systematically.
A proper textbook, almost?
Kind of. But the real science of why iron behaved differently based on carbon content, that was still a long way off. It was mostly practical know-how.
Okay, fast forward to the 18th century. The Industrial Revolution is kicking off. Iron seems absolutely central. What was the big breakthrough?
The absolute game changer was using coke instead of charcoal in the blast furnace.
Coke, made from coal.
Exactly. Coal heated without air to drive off impurities. Abraham Darby at Coalbrookdale in England successfully did this around 1709.
Why was that so important?
Because England was running out of trees for charcoal. Charcoal was getting expensive, but England had loads of coal.
So a cheaper, more abundant fuel source.
Precisely. Coke smelted iron got better quickly, and it was much cheaper. This suddenly made large-scale iron production feasible in a way it hadn't been before. It provided the affordable iron needed for steam engines, for machinery, for the first railways. It fueled the Industrial Revolution.
Darby's innovation unlocks mass iron production, and this iron then enables other key technologies.
Absolutely. Think of James Watt's steam engines. They needed accurately bored iron cylinders. John Wilkinson developed better boring machines, partly for cannons, but also perfect for Watt's engines. Iron was enabling precision engineering.
But they still needed good steel, right? For tools, springs, things needing hardness.
Yes, the demand for quality steel was growing too. And around 1740, another breakthrough, this time in Sheffield, England. Benjamin Huntsman perfected crucible steel production in Europe.
Crucible steel, like the Indian wootz process?
Very similar idea, yeah. Huntsman took existing steel, melted it in sealed clay crucibles to get a really uniform, high-quality molten steel. He could then cast this into ingots.
And Sheffield crucible steel became famous.
World famous. It was perfect for clock springs, cutting tools, surgical instruments, and of course Sheffield cutlery. It gave Britain a big edge, but It was still a small batch process, expensive. It couldn't meet the massive demand for steel that was coming in the 19th century.
Ah, the 19th century. Railroads booming, factories everywhere, bigger ships. This is when steel really takes over. The age of steel.
That's what they call it. Though initially, a lot of those rails and bridges were still made of wrought iron, produced by the puddling process.
Puddling. What was that?
It was another way to refine pig iron into wrought iron, developed by Henry Cord in the 1780s. You stirred molten pig iron in a furnace to burn off carbon. It made better wrought iron faster.
So good wrought iron was available, but people wanted steel for its strength.
Exactly. Engineers knew steel was stronger, more durable, but it was just too expensive and slow to make in large quantities using crucibles. That was the bottleneck. Until 1856.
1856? That sounds significant.
Henry Bessemer, the
It
Bessemer converter.
Right. The name everyone knows. What was his big idea?
It was brilliantly simple, in hindsight. He realized you could burn the carbon out of molten pig iron just by blowing air through it.
Blowing air through molten iron. How did that work?
You poured molten pig iron into this big pear-shaped vessel converter, then blasted compressed air in through the bottom. The oxygen in the air reacted violently with the carbon and silicon in the iron.
Creating a lot of heat and fire, I imagine.
A spectacular display. Sparks, flames. The reaction generated its own heat, burning off the impurities, especially carbon. And it was incredibly fast.
How fast?
Bessemer demonstrated converting several tons of pig iron into steel in about 30 minutes.
30 minutes
Yeah.
compared to hours or days for crucible steel.
Exactly.
Right.
Suddenly, you could make large amounts of steel relatively cheaply. It produced what we call mild steel, low carbon, very versatile. This was the start of truly mass steel production.
And steel prices must have plummeted.
Dramatically.
Yeah.
Steel went from being a specialty material to a bulk commodity. Bessemer converters popped up everywhere, especially in Sheffield, then America, Germany. Steel output just exploded.
Bessemer became a superstar inventor, I guess.
Oh yeah, hugely famous. His process was adopted rapidly, especially in America, by people like Andrew Carnegie in Pittsburgh.
Were there any downsides to Bessemer steel initially?
Yes, the original process didn't work well with iron ores containing high levels of phosphorus, which made the steel brittle.
Ah, so they needed specific types of iron ore.
Initially, yes. But that problem was solved later, around 1878, by Sidney Gilchrist Thomas, who came up with using a basic lining, usually dolomite, in the converter. This basic lining reacted with the phosphorus and removed it into the slag.
The Thomas process, right, so that opened up more ore types.
Exactly. It made Bessemer-type steelmaking viable with a much wider range of iron ores. By 1900, global steel production was massive, driven largely by Bessemer and Thomas steel, especially for things like railroad tracks.
So Bessemer revolutionized things, but there was another mass production method developed around the same time, the open hearth furnace.
Yes, the Siemens-Martin process, or open hearth furnace, developed in the 1860s. It was a different approach.
How did it work?
You melted pig iron, scrap iron, and other ingredients on a large, shallow hearth, kind of like a giant shallow basin inside a furnace. It used preheated gas and air to reach really high temperatures.
Okay, so melting on a hearth instead of blowing air through it. What were the advantages?
It was slower than Bessemer, taking maybe 6 to 12 hours per batch or heat, but it gave much better control over the steel's final composition. You can test samples during the process and make adjustments.
More precise quality control.
Yes. And critically, it could melt large amounts of scrap steel along with the pig iron. That was a big economic advantage, recycling scrap metal.
So Bessemer was fast, open hearth was slower but more controlled and used scrap. Did one win out?
For a long time, they coexisted. But the open hearth process became dominant for producing higher quality structural steels, the stuff needed for bridges, ships, and especially early skyscrapers.
Ah, so the steel skeletons of buildings like the Flatiron in New York, that was open hearth steel.
Mostly, yes. Well, the Eiffel Tower is famously wrought iron. The age of steel skyscrapers really relied on the consistent large batches of quality steel the open hearth could produce. It remained the leading process for many steel types well into the mid-20th century.
This explosion in steel production, it must have totally transformed landscapes and societies, creating huge industrial centers.
Absolutely. Cities like Pittsburgh, Steel City, or Essen in Germany's Ruhr Valley, they basically grew up around these massive steelworks. They drew in huge numbers of workers, often immigrants looking for jobs.
And the work itself, in those mills.
It was incredibly tough. Hot, dirty, dangerous long hours. It created a vast industrial working class and eventually powerful labor movements fighting for better conditions.
And this era gave us the titans of industry, right? Like Andrew Carnegie.
Carnegie is the classic example in the U.S. He built an empire, Carnegie Steel, dominating production through efficiency, technology, and, well, ruthless business practices.
He made steel cheap and plentiful, especially for rails.
Yes, his mills churned out rails that built America's railways. He eventually sold his company to J.P. Morgan in 1901, forming the giant U.S. Steel Corporation.
But this industrial power often clashed with the workers, didn't it? The Homestead Strike comes to mind.
Homestead in 1892 is a brutal example. Carnegie's manager, Henry Clay Frick, cut wages and tried to break the union. The workers struck. Frick hired Pinkerton guards.
And it turned violent.
Very violent. A pitched battle between workers and Pinkertons. People killed on both sides. Eventually, the state militia came in, the strike was broken, the union crushed. It showed the raw power struggles of the era.
A really dark chapter. Were there any more positive developments for workers later on?
There was some progress, slowly. Things like company towns offered amenities, often with tight control. And you had figures like Jamsetji Tata in India.
Tata Steel.
Yes, he founded Tata Iron and Steel in 1907, Asia's first big integrated plant. But he also planned the town, Jamshedpur, with schools, hospitals, a more holistic vision, though still within a company framework.
Interesting. And other countries were building steel industries too.
Oh, yes. Japan's Meiji government started Yawata Steelworks. Russia had state-owned ironworks. In Germany, you had Alfred Krupp building a huge industrial empire, heavily focused on steel, especially for armaments. Steel was truly global and fundamental by the early 20th century.
So heading into the 20th century, steel is king, but its role becomes even more intense with the world wars.
Absolutely. The 20th century showed steel's dual nature. Immense power for destruction in war, but also essential for rebuilding and progress in peace.
World War I.
Steel was critical. Artillery shells, battleships, later tanks. The war pushed innovation in alloy steels, too, for armor, for aircraft engines. Metallurgy became a key part of military strength.
And between the wars and after World War II, steel for building.
Definitely. Rebuilding after WWI, then the Depression, then massive post-WWII reconstruction, skyscrapers like the Chrysler and Empire State Buildings, bridges like the Golden Gate, all steel framed. Plus cars, appliances, consumer goods relied on steel.
Henry Ford used special steel in the Model T, didn't he?
Vanadium steel, yeah. Made it lighter and tougher, showing how specific alloys were becoming important even in mass production.
And World War II, even more of a steel war.
You could say that. Allied steel production, especially the U.S., just dwarfed the Axis. Think Liberty ships, churned out using prefabricated steel sections, Sherman tanks, aircraft engines using high-strength steel alloys.
Though aircraft started using more aluminum too, right?
Yes. The war showed steel's limits too. Aluminum was lighter for planes. And anti-tank weapons got better, demanding ever thicker armor. But steel was still the backbone.
After WWII, was there a boom time for steel?
Huge boom. The golden age, some call it. Reconstruction in Europe and Japan, massive consumer demand in the U.S. Steel mills ran flat out, and steelworkers, often through strong unions, saw pretty good wages and conditions in many places. It was a path to the middle class.
But technology didn't stand still. What came after the open hearth furnace?
The next big leap was the basic oxygen furnace, or BOF, starting in the 1950s.
Basic oxygen. How did that work?
Instead of just air, you blast pure oxygen at high speed onto the molten pig iron using a water-cooled lance. It's much faster and more efficient at burning off carbon and impurities.
Faster than open hearth.
Much faster. A large BOF could make hundreds of tons of steel in under an hour. It also generated enough heat to melt a lot of scrap steel along with the pig iron.
So faster, efficient, used scrap. Sounds like a winner.
It was. BOFs rapidly replaced open hearth furnaces worldwide from the 60s onwards. Most open hearths were gone by the 80s.
And what about recycling scrap? Was there another technology focused on that?
Yes, the electric arc furnace, or EAF. It had been around much longer, but really took off in the later 20th century for scrap recycling.
How does an EAF work?
It uses huge graphite electrodes to pass an electric current through scrap metal, creating an arc that melts at very high temperatures.
And its main advantage is using scrap.
Primarily, yes. EAFs don't need iron ore or coke. They're great for turning old cars, appliances, construction debris back into new steel. That's often used in smaller mini-mills.
So BOF for primary steel from iron ore, EAF mainly for recycling scrap.
That's generally how the industry evolved. EAFs now account for a significant chunk of global production, especially for things like rebar.
Beyond the basic production methods, the types of steel themselves have become incredibly diverse, haven't they? All the alloys.
Oh, absolutely. That's been a huge story in the 20th and 21st centuries. We had early alloys like nickel and chromium steel, but then came stainless steel.
Invented by Harry Burleigh in 1913, adding chromium for rust resistance.
That's the one. Game-changing. Then you get high-speed steels for cutting tools that stay hard even when red hot. Silicon steels for electrical transformers. Super strong, miraging steels for aerospace. The list is endless.
Thousands of different steel grades today.
Easily. Each engineered for specific properties: strength, flexibility, hardness, corrosion resistance, heat resistance, whatever the application needs.
And even in everyday things like cars, the steel has changed dramatically.
Totally. Compare an old car's heavy steel panels to modern cars using advanced high-strength steels AHSS.
Much stronger so they can use less of it.
Exactly. You get lighter cars, which means better fuel economy or longer electric range, but they're also safer in a crash because the steel is engineered to absorb energy in specific ways. It's all about controlling the steel's microstructure.
And now we're even talking about engineering steel at the nanoscale.
Right, the cutting edge, yeah. Nanostructured steels. By controlling the grain size down to billions of a meter, researchers are creating steels with incredible strength, sometimes double or triple conventional high-strength steels, but still keeping some ductility so they don't just snap.
Wow. What could those be used for?
Huge potential. Lighter vehicles, stronger structures, maybe even new kinds of tools or wear-resistant parts. It's still mostly lab scale, but very exciting.
It's an amazing journey. But the environmental impact. Steelmaking, especially the traditional way with blast furnaces and coal, is a huge source of CO2 emissions, right?
That's the massive challenge for the industry today. Steel's essential. We make almost 2 billion tons a year globally, but traditional primary steelmaking is very carbon intensive. Sustainability is now a central focus.
So what's the path towards greener steel?
One of the most promising routes is using green hydrogen.
Hydrogen instead of coke. How does that work?
The idea is to use hydrogen, produced using renewable electricity, that's the green part, as the reducing agent to strip oxygen from iron ore. Projects like Hybrid in Sweden are pioneering this.
And the byproduct isn't CO2.
Exactly. It's just water vapor. H2 plus iron oxide gives you iron plus H2O. So the iron-making step could become essentially carbon-free. Then you melt that hydrogen-reduced iron, DRI, in an electric arc furnace powered by renewables.
A potential path to near-zero emission steel. Is it happening yet?
The technology works. H-White has produced fossil-free steel. The big challenge now is scaling it up and making it economically competitive. But projections suggest hydrogen could be a major part of steelmaking by 2050.
That's huge. What else is being done? Recycling more?
Absolutely vital. Steel is endlessly recyclable without losing quality. Using scrap in an EAF saves about 75% of the energy compared to making steel from ore. Currently, maybe 30% of steel is made from scrap globally, but increasing that percentage and improving collection is key.
Can existing blast furnaces be made cleaner in the meantime?
There are efforts, yes. Injecting biomass or natural gas to replace some coke. Developing carbon capture technology to grab the CO2 before it leaves the smokestack, although that's complex and expensive. Some plants are integrating renewable energy, like using solar power for EAS.
So multiple strategies working in parallel. And steel itself can help sustainability too.
Yes, through its use. Those advanced high-strength steels make cars lighter and more fuel-efficient. Stronger steels allow for taller, more efficient wind turbines. Steel is part of building a more sustainable infrastructure, paradoxically.
It really is an incredible story, full circle in a way. From mysterious space metal to a material potentially made cleanly with hydrogen.
It's a testament to human ingenuity, isn't it? Constantly adapting the material to our needs, and now adapting the process to our environmental responsibilities. The story of iron and steel is far from over. It's still being forged.
A final thought then. This journey, from those gifts from the sky to the potential of green steel, it's more than just metallurgy. It's a saga of innovation, labor, industry, power, and now a real reckoning with sustainability. It's about how we forged not just metal, but our entire civilization. So, next time you see a steel beam or use a simple steel tool, maybe pause and think about that incredible history packed inside it.
And looking forward, you have to wonder. With materials science advancing so fast and the push for sustainability only growing stronger, what's the next big transformation in this ancient story of iron and steel going to be?
Definitely something to ponder. We hope this deep dive sparked your interest. Maybe look into ancient smelting techniques or the drama of the Industrial Revolution's steel barons or the cutting edge of green steel tech today. There's so much more to explore.